Hydroboration-oxidation reactions. So, hydroboration-oxidation reactions are reactions that start with alkenes and form alcohols. The reaction consists of two parts: the hydroboration step, where usually BH3, which is extremely reactive molecule because of its lack of an octet around its central atom, and the THF molecule, which is used to stabilize the BH3 because of how reactive it is, are added to the reactant in the oxidation step, where H2O2 and OH- are added to the molecule. In the hydroboration step, a hydrogen bond bonds to a carbon-carbon or carbon-nitrogen double bond, as is seen here. The resulting carbon-boron bond is stable because of its similar electronegativities between carbon and boron, 2.55 and 2.04, meaning that it is also easily polarizable. Hydroboration's regiochemistry is anti-Markov process because the hydrogen bonds to the most substituted carbon, the carbon with the fewest carbon-carbon bonds, of the alkene double bond, and the boron bonds to the least substitute carbon of the double bond because this path follows the least steric hindrance, or resistance from the other carbons. While the stereochemistry of hydroboration is syn, which means that both new bonds are on the same face as the alkene. The addition of BH3 to the molecule is a four-member transition state, and the reaction or the breaking of the double bond between the two carbons and forming of bonds between the boron and the carbon occurs all at once, meaning that when it bonds to carbon, it forms a partial negative charge in this carbon-boron area, whereas it forms a partial positive charge over here since the electrons are attracted to this carbon-boron bond over here. The partial positive charge on the carbon attracts the negative charge of the hydride, a hydrogen with 2 electrons, from the BH3 molecule, forming a bond with that carbon. This forms a trialkylborane molecule. Next step, oxidation step, the molecules react with H2O2 and an OH- ion, which acts as a base and takes on an H+ ion from the hydrogen peroxide, as is seen in step 2. Here you see the hydrogen peroxide acid taking on a hydrogen, or donating hydrogen to the hydroxide, forming an H2O molecule and hydroperoxide ion. This new molecule acts as a nucleophile which attacks the boron atom of the trialkylborane. A bond forms between the boron of the trialkylborane and the oxygen of the hydroperoxide ion, and a bond is broken between the oxygen and the oxygen of the hydroperoxide ion, which causes the hydroxide ion to break off. This is seen right here, where the hydroperoxide ion forms a bond with the boron, and this causes in step 4, this causes a bond to break between the boron and the carbon over here, and a bond to form between the oxygen and the oxygen over here, which then results in this molecule over here. In the next step, the hydroxide ion of an NaOH molecule attacks the boron, breaking the bond between the boron and the oxygen, and forming a bond between the hydroxide molecule and the boron. This is seen over here, where, as you can see, the hydroxide forms a bond with the boron then breaks a bond with the oxygen, so the boron leaves the molecule with the hydroxide ion, leaving behind an negatively charged oxygen, which then forms a bond with the H2O molecule over here, which then breaks the bond between the hydrogen and the oxygen of the H2O molecule. In the end, it forms this product over here, which ends up being a hydroxide molecule over here. The product of this reaction is racemic, meaning that this molecule over here has an enantiomer that forms 50% of the time during a reaction. So a comparison I found between the hydroboration-oxidation reactions, I found it similar to editing or revising a Lego structure. I found this similar because the hydroboration-oxidation reaction starts out with an alkene molecule, and through several steps and reactions of forming and breaking chemical bonds, the original molecule structure and functioning is altered. Similar to the Lego blocks, since the starting molecule or starting structure doesn't have to consistently be the same, as long as the Lego creation has some key structures. The Lego blocks can be added onto or taken off of it. This is similar to the reaction how initially you start off with an alkene, which can be a number of different molecules, including both chain and ring alkenes. Then throughout the reaction, certain atoms are added or removed from the molecule to create the end product, as is seen here. So there are multiple applications to this reaction. The reaction is used to produce various organic compounds or organoborane molecules with carbon-boron bonds. This reaction is frequently used because of its high versatile and powerful reaction, so it can create a wide range of wanted organic molecules. This is important because for fields whose purpose is to synthesize new organic molecules, this reaction is very useful. Therefore, this reaction is important because it is so versatile and can form a wide range of products depending on the reactant used. These reactions are frequently used for addition or synthesis reactions, where through multiple processes an atom or compound is added to an organic molecule, forming a new molecule. Thank you.